All right, everyone, welcome. Today, we're going to dig into the absolute heart of all electronics, the electric circuit. We're going to move past just knowing it works and really get into the principles that let us control energy and, power pretty much everything around us. You see this stuff in action all the time, right? You flip a switch, the lamp turns on. It feels simple, almost intuitive. But here's the thing. For us, as engineers, intuitive just doesn't cut it. We need rules. We need predictable, quantifiable principles to actually build things. Exactly. So to really engineer solutions, we have to pull back the curtain on that magic and understand the machine underneath. What are the rules that actually govern this flow of energy? That's what we're here to figure out. So let's jump right in. Okay, so first things first. Every single functional circuit, I don't care if it's in your phone or in a simple flashlight, it all boils down to three essential elements. These are the non-negotiables, the absolute must-haves for any system that's going to do work with electricity. So what are they? Well, first, you've got to have a voltage source. That's your push. Think of a battery. Second, you need a load, something to actually do the work, like the lamp bulb. And third, and this is crucial, you need a complete conductive path for that current to flow. If you're missing even one of those, you don't have a circuit, you just have a pile of parts. The real engineering problem then is how do we control the energy that's flowing through that path? Think about it. What would happen if we just connected a battery straight to a wire with nothing else? Well, you'd get a massive, uncontrolled rush of current, basically a short circuit. The only thing stopping it would be the tiny, tiny bit of resistance in the wire itself. To prevent that and actually manage the flow, we have to use this fundamental property that all materials have: resistance. Yeah, you can really think of resistance as a kind of electrical friction. As those electrons try to zip through a conductor, they're constantly bumping into and colliding with the atoms of the material. That opposition, that friction, is what slows them down. It's what limits the current and, most importantly, allows us to actually harness that energy and do useful work in a controlled way. And here's the really cool part. This property isn't just some random thing. It's built right into the material's atomic structure. You look at something like copper, it's got these 1 to 3 valence electrons on the outside that are just barely hanging on. They're easy to push around, which makes it a great conductor. But then you look at an insulator, it's got more than 4 of those electrons, and they are held on tight. They don't want to move, which is why they're so good at blocking current. Okay, so since this whole resistance thing is so absolutely critical for controlling current, we can't just leave it up to chance, right? We can't just hope the wire has the right amount. No way. So what did we do? We engineered components, we call them resistors, specifically to add exact, predictable amounts of resistance right where we need it in a circuit. And a classic example of this is the carbon composition resistor. It's brilliant, really. Manufacturers just mix finely ground carbon, which is conductive, with some insulating filler. By tweaking that recipe, that ratio, they can dial in a super specific resistance value. It's a perfect example of how material science is directly applied to make electronics work. All right, so let's take stock. We've got our source, our load, a path for the current, and we even have a way to control how much current flows using resistors. But how do we turn it on and off? How do we intentionally start and stop that flow? That brings us right to the fundamental idea of open and closed circuits. The switch is really the most straightforward form of control you can imagine. When a switch is off, it's literally creating a physical gap in the wire. Think of it like an open drawbridge. The path is broken. That's an open circuit, and no current can flow. But when you flip that switch on, you close the bridge. The path is complete, and boom, you have a closed circuit. Current flows, and the lamp lights up. It sounds incredibly simple, doesn't it? But this is a profound rule that is the foundation for all of electronics. For electricity to actually do any work, those electrons have to have a complete, unbroken path. They have to travel from the source, go through the load, and make it all the way back home to the source. It's all about the complete loop. So, building a circuit that just works, that's step one. That's the easy part. But building one that's actually safe and reliable, that requires us to think about a couple more essential ideas. We need to talk about protecting it from too much current and giving it a stable reference point for all its voltages. This is where fuses and circuit breakers come in. At the end of the day, they both do the same job. They're overcurrent protection. Their entire purpose is to fail safely by creating an open circuit if the current gets too high. The main difference? A fuse is kind of like a kamikaze pilot. It's a one-time deal. It melts and has to be replaced. A circuit breaker, on the other hand, is just a resettable switch, which is obviously way more convenient in most cases. And this process is totally automatic and absolutely vital.
Let's say a component fails or you get a short somewhere. That current is going to spike. That protective device is designed to react in milliseconds. Bam! It opens a circuit and stops everything. And that's what prevents the wires from getting red hot and, potentially starting a fire. It's a critical safety feature.
Okay, our final core concept here is ground. Now, electrically speaking, ground is simply our designated 0-volt reference point. Think of it like sea level. We measure all the mountain's heights relative to sea level, right? In a circuit, we measure all the other voltages relative to this common 0-volt point. This is what gives the whole system stability and makes sure everything is operating from the same playbook. And a perfect real-world example of this is your car. The entire metal frame of the car is connected to the negative terminal of the battery, making the whole chassis the ground. But what does that really mean? It means it also acts as the return path for the current. That's why a component like a taillight only needs one wire running to it for the positive voltage. The current does its job lighting the bulb, and then it finds its way back to the battery right through the metal frame of the car. Pretty efficient, huh? So look how far we've come. We started with just watching a light turn on, which felt like magic. And now we've broken it all down into a real engineered system. We've identified the core components, source, load, path, and we've layered on the critical elements of control and safety, resistance, switches, and all that protective gear. We're moving from it works to how and why it works. But here's the thing. This conceptual understanding, this qualitative stuff, it's only the beginning. To really design, to analyze, to predict how a circuit will behave, we have to go from words to numbers. We need to get into the calculations. In answering that question, how do we do that? Well, that's going to lead us straight to the mathematical relationship that is, without a doubt, the most fundamental law in all of electrical engineering.